Hey guys, welcome back to part 5 of the how to implement the FFT tutorial for audio programmers. In the last video, we made an amazing accomplishment. We made an in-place FFT which is super applicable to, audio programming. Very efficient FFT compared to the recursive one we did before. I don't know why you would watch this video if you haven't watched any of the other ones. This is about optimizing the in-place FFT and implementing the inverse, which is trivial. But anyways, yeah, this video is going to be about optimizing the in-place FFT. So let's go ahead and jump right into it. This is the same code from last time, and as you can see, it produces the same output as the recursive FFT, and although it seems to be a little bit different, more floating point errors, I have a feeling that's because if you see these are float 32 arrays up here, I must have done that explicitly, and then down here it's just arrays of numbers. I don't know if there's a size difference that's an issue, or maybe it's just a formatting thing, but yeah. Anyway, they're the same, effectively. So, with that, let's go ahead and optimize this code a little bit. So I'm going to make some more room over here. Alright, so where can we start with optimization? Generally, how do we even think about it? Well, we think about expensive operations. For example, cosine and sine are pretty expensive operations, right? They take a while, and we do it a bunch of times. Although this is a lot quicker, and we use a lot less of them than in a normal DFT, we still use them, I think, too much, and many others think too much. So we can find ways to optimize this. But how, specifically? Well, I'll go ahead and give you guys a big hint. Watch what happens when I look at omega, right? Oh. Yeah, you can see that it's even bin, right? I thought I gave something away, but I didn't. That's why I was laughing. But as you can see, this is just the bin, right? But check this out, right? I mean, we know that we want to sample based on our bin, but look what happens when I put in even lm instead of even bin. Nothing, right? Nothing happens. It's a trick question. Now, what does that tell us? Well, that means that this is only really reliant on even lm, not the particular even bin. And why? Well, let me pull up the butterfly chart from last time. If you think about it in terms of each group, right? Remember that we're sampling with a sample frequency of 1 over these over 4, right? In this particular instance in stage 2, right? 1 over 4. So basically we're sampling with a frequency where 2 pi over length, but it's not 2 pi over this entire length, it's 2 pi over the length of the group, which is 4, right? And so then we have our 0th, our 2nd, or 1, our 2, and our 3. And essentially, that's all the bin number is. And when we go here and we have even bin, and hopefully you guys get this, hopefully it makes sense to you, our even bin, right, is actually going to be 4 plus 1, right? That's how we calculate it. But the thing about sine waves and cosine waves is, let me just draw something for you, right? We have a wave. Well, after that, right, here's 1 period. So after this point, and this point are exactly the same. And that's what we were doing. We were just taking here, the even bin is different, right? This is 4 and this is 0. But they align like this, where they are the same value, at least in terms of cosine and sine waves, right? So that means that it really does, like we just discovered, only really depend on even LM and not even bin. So okay, what's the point of doing that? Well, that means that why don't we just switch these for loops, right? Because we can pre-calculate this. So let's go ahead and do that. Let's just switch these for loops out, and let me just have this open. Right, so we just switched the for loops, and we still have the exact same thing, like I just said. So, okay, that was a fix. What does that mean, though? Well, it means that let's take omega out and put it up here. Okay, so we do that, and nothing changes. But now, here's the thing that's kind of cool, right? Well, all we're doing is taking cosine based on omega and sine based on omega. Let's just do that a little bit earlier. So I'm going to have what are called cosine omega, and this is going to be equal to the cosine of omega. And then we're going to have sine of omega equal to the sine. Sine omega. Okay. And now, instead of calculating these every time, we're just going to put them here. These are pre-calculated values. Right? So this is a big advantage that we've done. We're doing significantly less, right? We're not doing, let's see, right? We're doing it a bunch of times in this loop. Now we don't have to do it once for each of any of these, right? So that is a pretty good optimization that we've just made. But we can actually do better, believe it or not. And this is going to maybe get a little bit, we're going to bring in some names that might not make sense, but this is kind of what, I guess, jargon they use for, I guess, like professionals who work with FFTs and stuff, and they're called twiddle factors, right? We're going to bring in what are called twiddle factors. What are they? Well, before I get into what they are, I just want you to know that they are basically cosine and sine components. Well, ish. And I'll explain that. So, let's think about what we're doing here, like I just said, right? So, we have a sample size for this particular group, right, of 4, right? And so what that means is I'm going to go ahead and just keep this wave, right, draw this wave. And now what I'm going to do is divide it into 4 pieces. So we've got one down the middle, and it should be right on the peak, right, and then one on the bottom. Alright, so we've divided this into 4 pieces, and we know that this piece and this piece are equal, right, based on what I just told you, right? But we divided this into 4 pieces. Well, what we're doing now is we're saying, okay, this is even value, right? This is, and it increments, right? It goes +1, or yeah, +1, +1, and then we calculate the bin frequency based on that. Well, this is really the same thing if we think about a circle, right? I'll do it in terms of a circle now, right? And we start here, and then these are our points that we go to. We're rotating by a constant value. We're rotating by a constant angle, right? And in this case, it's 90 degrees that we're rotating by. So what does that mean? Well, it means that instead of calculating new sine and cosine components for each even element, right? And I misspelled, it's not even val, it's even element, right? Instead of recalculating the cosine and sine positions for each time we increment even element, why don't we just rotate by 90 degrees? And what is the benefit of that? Well, we know the rotation formula. And let's see if I can pull it up here. Yep, here it is. Right, x cosine, this is how you rotate by any theta. And this doesn't involve, well, it does involve cosine and sine, but you'll see why it doesn't. When we rotate by a constant theta, we just have to calculate cosine theta and sine theta once, right? And we can rotate 4 times by that same value without having to recalculate it. So we do have to calculate cosine and sine theta, but we only have to do it once for each, right? All right. Cool. So now we know that instead of recalculating the sine and cosine multiple times, we're just going to rotate, which we can do with that rotation formula, which is what we're doing in our DFT anyway. All right. So, what is the point of that? Well, the point of that is to essentially pull this out of here and put it up here. And so, yeah, we're going to get some errors because we don't have even element yet, right? But now here's what I'm going to do, right? We don't need this anymore, right? This is equal to, let's take a look at this again. One of these is the difference, which is the same as this, right? Like whatever 2 pi over the separation is, right? And separation is equal to the group size, remember that. I'll even write that here. So, right, we have 4, right? And then we have this frequency here. This is equal to 1 step, right? So this is all we need to know, and then we can make the so-called twiddle factors. So I'm going to call it twiddle real, and this is going to be the cosine of omega, and twiddle imaginary is going to be the sine of omega, right? Okay, so now you'll notice that we've done this twice. Well, what does this mean? Well, we know that we are always starting at 0, right? For all of these calculations, we always start at 0. So what does that mean? That means that we know the cosine and sine we're going to start with. So we know the cosine of 0 is 1 and the sine of 0 is 0. Okay, so that's great. But now here's where this gets really cool, right? After every increment of even LM, we're going to go down, and instead of recalculating cosine and sine like we were before, we're actually just going to rotate our cosine and sine using twiddle factors. So let's go ahead and we'll need a temporary variable, and we'll just make it equal to the last, actually I'll call it old cosine omega, and it's going to be equal to the previous cosine omega, and then we'll set that equal to the rotated version of it, and we know that formula. In fact, it's right here in the Fourier transform. So we've got x times cosine minus y times sine, right? So what is x in this case? Well, it's the twiddle real factor times cosine, right? And then minus the imaginary twiddle factor times the sine. All right, cool. And then we need to set sine omega, which is going to be, like we already know, the sine plus the cosine. And actually, this has to be the old cosine. And I spelled it wrong. And boom, believe it or not, that actually gives us the same exact fast Fourier transform. All right, so that's pretty cool, isn't it? Using this rotation technique, because now we only have one cosine and one sine calculation for every stage. Now that is a big save if you ask me. Now what's even cooler is you can actually pre-calculate these if you really want to. And then you have 0, right? So that would be the most ultimate ideal thing you could do. But I don't know, to me that's good enough, right? I think we've made some pretty good optimizations. There's another really important optimization that I want to make, and it's instead of using arrays of arrays to represent this, right, or an array of arrays, what we can do is, instead of having an array of arrays, right, that and the inside arrays have a real and imaginary component, what we can do is, for spatial locality, which is a term that means basically when we load things to and from memory, we can make them adjacent. And so we can do one of two things off the top of my head. We can either put the real and imaginary component next to each other in the array, or we can put all the real components first and then the imaginary components second, which I think would be the superior method to do. And that's stuff I do because I've done this before. So what I'm going to do is comment out this FFT because it's no longer going to work. And instead of doing what I've done with these mini arrays, I'm going to have all the real components first. So 0, 0, 0, 0, 0, 0, 0, 0. And making sure it's a power of 2 again. We're sending in now this array, so now we just need to update everything in here. And so there are some things we have to fix. First off, this length is not true, or not correct anymore. So really the length is going to be half of the input length. So I'm just going to divide this by 2 because the second half contains imaginary components. Alright, so we have the length over 2 now, and basically when we do this bit swapping, we're going to do the same thing, except we don't need to go bit swap for a bigger length, right? We're bit swapping with the same length, which is really half the length now. But it needs to be that half length and not the full length, otherwise it's going to switch the imaginaries and the reals, and it's going to break the whole algorithm. So we're going to keep it with that old length, which is half the length. And we're also just going to put the new imaginary values at the new index plus length, right? So I just need to now add plus length here, and then just add this for all these values. Cool, and as you can see now, it's only done the shuffle with the reals and imaginaries separately. Okay, and so now we just need to fix up this part, which I will do with the replace function here in VS Code. And so I guess I do this, and then I just get rid of 0, right? Because that is going to be yes, that's going to be correct. And then I'm going to do 1, and it's just going to be plus length. Alright, and then I'm going to do the same thing, but with odds. And the same thing, but with plus length. Alright, and as you can see, now we go 28, -4, -4, -4. So it looks like everything has retained its workingness. And now we're better, I don't know, I don't want to sound too complex. This is just better, it's more efficient code that we've done. for doing this. Because if you had a pointer to a pointer, let's say, that's a lot of random loading from different memory for languages like C. Alright, so we have this, and I think in my head that we are in a good place with this FFT in place. We've done a lot of optimizations, great optimizations. I would time it for you, but in JavaScript the timing is off just because of how it's working with the web server and the because I'm hosting this with some VS Code plugin, but also JavaScript itself is not super quick, and also the web browser makes it slow sometimes. So I don't know. Anyway, yeah, this is a pretty well optimized in-place FFT algorithm. I don't know if it's production level, but it's probably pretty close. And finally, I'll go ahead and implement the inverse. Why not? So we'll have inverse, right? We're gonna make a we're just going to store this in this. We're going to add a flag that says if it's inverse or not, and we're going to say first time no, and then we're going to log it, and then we're going to log the FFT in place of it where we do the inverse Fourier transform. All right, and so we have this flag that says inverse. Now the only thing we need to change, we've already done this with the discrete Fourier transform, so hopefully you know that by now. Basically, we'll just add this variable called direction, which will be either positive or -1. And so if we're doing the inverse, then we want to make it 1, otherwise -1 like we have been doing, and then we'll say direction here. All right, cool. And then if you notice, we're almost there. We just need to actually divide by the length. So if inverse for, I could do a for each loop, but why not? This is closer to C++. Divided equals by length. Oh, whoops, why did I say that? And there we go. We got 0, 1, 2, 3, 4, 5, 6, 7, and then a bunch of essentially zeros. Alright guys, well that's pretty much all I have for this FFT for Programmers series. Maybe I'll make a summary video or something, but yeah, I've shown you guys a lot. We've learned a lot. I've learned a lot even doing this. So I hope you guys use this. I hope you guys tell your friends who are interested in this. I know a lot of people may not actually be interested in this, but I was really sort of fixated on figuring this out and looking at a lot of scholarly stuff. And it took a while for it to click, but I hope I showed you guys a unique perspective on the Fourier transform and the fast Fourier transform. And also giving you some useful tools, specifically with this in-place algorithm. But yeah, I think this might be the last video, so this is the end of my first series, I guess. I'm really, I feel like this is really good knowledge. I hope you guys use it, I hope you guys have fun with it. Definitely leave a comment if you have any questions, comments, or critiques. Not just for me, but for others. But yeah, I really appreciate you guys watching. Stay tuned for some more content. By the time this is posted, I'm going to hopefully be starting with some videos on actual audio plugin development with the Steinberg SDK for creating VSTs. But yeah, that's basically all I have for this tutorial series. Again, leave questions and comments in the comments. Thank you guys for watching.